Ever try to juggle like a ton of tasks all at once?
Oh, yeah.
You're probably using a mental version of stack and heap memory without even realizing it.
It's true.
That's right. And today we're diving into an Algo Academy blog post all about this. Well, it's a crucial programming concept.
Absolutely.
So we'll unpack why it matters for your code, what it means for its efficiency, and maybe even how it mirrors our own brains a bit.
Yeah, it's pretty wild. The way computers organize memory, it really does. It has a surprising parallel to how we manage information.
Right.
And getting it right, well, it's just key to making sure programs don't, crash or waste resources.
Totally. So first things first, what exactly is memory allocation when we're talking about computers?
Well, it's essentially reserving space in the computer's memory just for your program to work with. It's like, when you go to a restaurant,
Oh,
a
okay.
busy restaurant,
Yeah.
and you claim a table, your program's kind of doing the same thing. It's like, hey, I need this much room to operate.
Okay, that makes sense. And this Algo Academy post, well, it dives into two main ways this happens, stack memory
Mm.
and heap memory.
Right.
Is it safe to say the stack is the more organized, efficient one?
Absolutely. The stack is like a super tidy, you know, like a super fast assistant. It has a set limit
Yeah.
determined by the operating system. But within that limit, it's like lightning fast at giving and taking back memory.
The post uses this analogy of a stack of plates.
Uh-huh.
Is that what makes it so quick? Like last in, first out structure?
Exactly. And, another thing that makes the stack so efficient
Yeah.
is that stack memory is contiguous, meaning, well, it's all in one block. Think of it like having all your tools laid out neatly on a workbench.
Okay. Yeah.
Everything's right there when you need it.
They have a place.
Yep.
So the C++ example shows simple variables being stored this way.
Right.
But what's interesting is they vanish once the function ends.
Yeah,
It's like temporary storage.
that's right. That short lifespan of variables on the stack, that's a key characteristic. It helps prevent clutter and keeps things running smoothly.
So if the stack is for quick, temporary stuff, what about when you need more space and flexibility? That's where the heap comes in, right?
Precisely. Think of the heap like a massive warehouse. You can store things of all shapes and sizes in there.
Right.
Now, it's not as organized as the stack, but it's much more adaptable.
So less like a workbench and more like a heap.
Yeah. Haha. And a key difference here is that the heap, while it can grow as needed, limited only by the available system memory. So this makes it perfect for large data sets or things that need to, stick around for a while.
Makes sense. But this flexibility comes at a price, right?
Right.
The post mentions that heap allocation. It's slower and a bit more demanding to manage. True. If the stack is like grabbing a pre-made sandwich,
Right. Yeah.
the heap is like making one from scratch. You have more control over the ingredients, but, well, it takes more time and effort, and you have to do the dishes afterward, so to speak. There was something in the post about manual deallocation.
Yes. In some languages, that's the trade-off for that flexibility. Failing to deallocate that heap memory, well, that can lead to memory leaks, which are like leaving the faucet running, Eventually, you'll have a problem.
Right, right. The C++ example really highlights that. It shows an array being created on the heap and then specifically deleted using delete.
Yeah, that manual cleanup, it's essential. In languages like C++ do, it's the programmer's responsibility to, avoid those memory leaks and keep things tidy.
Okay, so we've got a good handle on each of them individually. But how do they compare head-to-head stack versus heap? What are the key takeaways here?
Well, the post has a handy table outlining the main differences. So the stack, right. Fixed size, fast, and automatically managed. Perfect for temporary data. But the heap, dynamic, slower, and sometimes requires that manual cleanup we were talking about. But it handles the larger or longer-lasting stuff. Which one you choose, well, it really boils down to what your program needs to do.
Like if I'm just making a quick snack, I'll use the countertop. But for Thanksgiving dinner, I need the whole kitchen.
Exactly. And speaking of different kitchens, the next thing to consider, well, it's how different programming languages approach stack and heap, because it's not always the same.
Right. The post mentions C, C++, B, Java, Python, and JavaScript. So are some languages more hands-on, while others take care of things behind the scenes?
That's a great way to put it. C and C++ Civ, for example, well, they give programmers a lot of control over both stack and heap allocation.
So it's like being given the keys to a professional kitchen. Amazing tools, but a lot of responsibility to use them correctly.
Precisely. C and C++ programmers, they need to be very careful about freeing up heap memory to prevent those, memory leaks we talked about. Now, Java, it takes a different approach, using something called automatic garbage collection.
Yeah.
Objects are allocated on the heap, but Java has a system to identify and reclaim unused memory automatically.
So it's like having a built-in dishwasher that cleans up after you.
You could say that. It makes life easier for Java programmers, but it's still important to understand how memory is being managed, to write efficient code, of course.
Of course.
Yeah.
What about Python? You're probably familiar with its reputation for being beginner-friendly.
Oh, absolutely.
Yeah.
Python, like Java, it utilizes garbage collection. It has a dedicated heap where everything is stored, and the Python memory manager handles the cleanup automatically. So yeah, it aims for, well, simplicity and readability, even when it comes to memory.
And lastly, there's JavaScript. What's the memory situation like there? Is it similar to Python?
In many ways, yeah. JavaScript also relies on a garbage collector to handle memory cleanup, although the specifics can vary a bit between, different JavaScript engines.
Okay.
The main takeaway here is that you don't have to manually deallocate memory. The system takes care of it for you.
Okay, so we've covered the differences between stack and heap, how they compare, and even how different languages approach them. But the post also talks about the consequences of getting this wrong. What are the real-world problems that can crop up if we mismanage memory?
Mismanaging memory, it's like a recipe for disaster. It can lead to program crashes, sluggish performance, unpredictable behavior. The Allocation post, it highlights 3 common issues: stack overflow, memory leaks, and dangling pointers.
Okay, let's unpack those. Stack Overflow, it sounds pretty intense, like my brain during finals week.
That's actually a pretty good analogy. It's what happens when you try to push too much data onto the stack, which, remember, has that fixed size limit. It's like piling books on a shelf. Eventually, it can't take anymore and collapses.
So what kind of coding scenarios would lead to that?
One common culprit: excessive recursion,
Okay.
where a function calls itself repeatedly.
Okay.
Each call, it adds another layer to the stack.
Okay.
And if it goes on too long, boom, stack overflow. It's a bit like those Russian nesting dolls, but with a less charming outcome.
Yeah, less charming for sure. The infinite recursion example in the post, it really drives that point home. Creating a huge array on the stack and then calling itself over and over. Talk about a recipe for disaster. Okay, so that's Stack Overflow. What about memory leaks? We touched on that briefly earlier.
Memory leaks, they're more insidious. They happen when you allocate memory on the heap. But don't release it when you're done. Imagine a program that creates temporary files, but never deletes them. Over time, the hard drive fills up, even though those files aren't needed anymore.
So it's not like a sudden crash, but more like a slow drain on resources.
Exactly. And in a program, this can lead to performance issues, slowdowns, and eventually even crashes if the system runs out of available memory. The code example in the post shows a function that allocates a big chunk of memory but forgets to deallocate it. Definitely a bad habit to get into.
Yikes, okay. So Stack Overflow is like a dramatic explosion, and memory leaks are like a slow poison. What about the last one? Dangling pointers. What makes them so dangerous?
Dangling pointers, they're tricky. They reference memory that's no longer valid. It's like having a map to a building that's been demolished. You try to follow the directions, but, you end up lost and confused, maybe even causing some damage along the way.
And in a program, that damage could be anything from unexpected behavior to a complete system crash, right?
Exactly. The example in the post, it shows a function that creates an integer on the heap, deletes it, but then still tries to use the pointer to that now freed memory. That's a classic, dangling pointer situation. Yeah. And, it can lead to all sorts of unpredictable problems.
Okay, so these memory problems sound pretty scary. What are some best practices that we can follow to keep our code, clean and avoid these issues?
Luckily, there are a lot of strategies that programmers can use. The Allocation post, it has a nice list. And they're all about, choosing the right tool for the job and being mindful of how you're using memory.
Yeah, let's hear them. Any tips from a memory management expert are welcome.
Well, the first one is simple, but crucial. Use stack allocation whenever appropriate.
Okay.
If you have small, short-lived data, the stack is your best friend. It's fast, efficient, and cleans up after itself.
It's like choosing a small backpack for a day trip. No need to haul a giant suitcase around.
Perfect analogy. Next, be mindful of object lifetimes. How long does this data need to exist? If it's just for a quick calculation, the stack might be fine. If it needs to, persist throughout the program, the heap is a better choice.
It's like planning a road trip. Snacks go in the car, camping gear goes in the trunk. Knowing how long you'll need something helps you pack efficiently. What other tips do you have?
For C++ programmers, smart pointers are a game changer. They help manage heap memory automatically, reducing the risk of leaks. Think of them like self-sealing containers that prevent spills and messes.
Sign me up for that. Anything that automates cleanup is a win in my book.
Another good one is to, well, avoid putting huge chunks of data on the stack. Remember, the stack has a limited size, so for large data sets, the heap is the way to go. It's like knowing, you can't fit a grand piano in your backpack, so you rent a moving truck instead.
Okay, that makes sense. Any other essential tips?
Absolutely. For languages that require manual deallocation, always remember to free up heap memory when you're done with it. It's like, washing your dishes after a meal. It keeps things clean and prevents problems down the line.
And if you want to be extra careful, there are tools that can help, right?
Yes. Memory profiling tools, they're like having a detective on your team. They can help identify memory leaks and other issues, giving you a clear picture of how your program is using memory.
So choose your tools wisely. Be mindful of cleanup. And don't be afraid to call in the experts if things get messy.
Got it.
But the Allocation post, it also mentions some advanced memory concepts that we haven't touched on yet. There's even more to learn about memory management.
There's always more to explore. Two fascinating topics. Well, memory alignment and fragmentation.
Okay, those sound a bit intimidating, but also intriguing. Memory alignment sounds like something from a yoga class.
Well, it's definitely a different kind of alignment. In programming, it's about, how data is arranged in memory. You see, computers, they have preferred ways of accessing data, often in chunks of 4 or 8 bytes.
So it's like the computer has a favorite way of organizing things. Maybe it's a bit OCD.
Something like that. Now, if data isn't aligned, according to these preferences, it can actually slow down memory access. It's like trying to read a recipe where the ingredients are scattered all over the page. It takes more effort to process.
The post uses an example of two C++ structs, align struct and pag struct. Can you explain what's going on there?
Certainly. The align struct, well, it's designed to follow the computer's preferred memory boundaries.
Okay.
While the pack struct it crams everything together, ignoring those preferences.
So even though pag struct might take up slightly less memory, it could actually be slower because it's not playing by the computer's rules.
Exactly. It's like trying to fit square blocks into round holes. Sometimes it's better to leave a little bit of space for things to line up properly. That's the essence of memory alignment, understanding these preferences and arranging your data accordingly to optimize access speed.
Makes sense. So that's alignment. What about memory fragmentation? It sounds like something that happens to a hard drive after years of use.
It's similar, but instead of a hard drive, it's happening to your program's memory. Fragmentation occurs when you have a lot of small, free memory blocks scattered throughout the heap. Think of it like a messy drawer full of loose items.
So even if there's technically enough space overall, it's not usable because it's all broken up.
Exactly. This can lead to problems because, when your program needs to allocate a larger chunk of memory, it might not find a contiguous space big enough, even though there's enough free space in total.
It's like having a bunch of small containers, but none of them are big enough to hold the leftovers from your dinner party.
The post breaks down fragmentation into 2 types, internal and external. Internal fragmentation is like when you allocate a big box for a small item, you're wasting space within the allocated block.
And external fragmentation is like having a bunch of small empty spaces,
Yeah.
but none of them are big enough to be useful.
Yeah.
So how do we deal with this messy drawer situation? Are there ways to combat memory fragmentation?
There are. One approach, is using memory pools.
Okay.
Especially for objects of the same size. It's like having designated compartments in your drawer for different types of items, socks, underwear, and so on.
Right.
This helps keep things organized and reduces fragmentation.
So organization is key, both in our physical spaces and in our digital ones.
Absolutely. Another technique, periodic defragmentation. It's like taking everything out of the drawer, sorting it, and putting it back in a neat and organized way, creating, larger contiguous spaces.
Like a digital Marie Kondo. Now, are there specific memory allocation strategies that can help prevent fragmentation in the first place?
Yes, some clever algorithms try to minimize fragmentation right from the start. The buddy system and slab allocation mentioned in the post, they're good examples. They allocate memory in a way that, reduces the chances of creating those tiny, unusable fragments.
So it's like having a system for packing your suitcase where you always try to fit things together snugly. Now, before we move on, I want to circle back to garbage collection, which we touched on earlier. Languages like Java and Python use it to, automatically reclaim unused memory. But what's happening behind the scenes? Are there different types of garbage collection?
There are indeed. And each type, well, it has its own approach to identifying and reclaiming that unused memory. With pros and cons to consider, of course. The post mentions mark and sweep, copying collection, generational collection, and incremental collection.
Wow, that's a lot of garbage collecting.
Yeah.
Can we break down those approaches a bit?
Of course. Let's start with mark and sweep. It's like doing a spring cleaning in 2 phases.
Yeah.
First, you go through and mark everything you want to keep, the valuable stuff.
So like putting sticky notes on all the clothes you're keeping in your closet.
Exactly. Then in the sweep phase, well, you get rid of everything that's not marked. Those are considered garbage and can be safely removed. So anything without a sticky note gets donated or tossed.
That makes sense. What about copying collection? How does that work?
Imagine having 2 closets.
Okay.
With copying collection, you move all the good stuff, the live objects,
Oh.
from one closet to the other, leaving all the garbage behind in the first closet.
So you're essentially transferring everything you want to keep to a fresh, clean space.
Precisely. This can be very efficient because, well, it compacts the memory and reduces fragmentation. But of course, you need the extra space of that second closet, which is a trade-off.
Okay, 2 closets, got it.
Yeah.
Now on to generational collection, which sounds super intriguing.
This one is based on the idea that, well, most objects in a program, they have a short lifespan. They're created, used, and then discarded relatively quickly. It's like those trendy clothes you buy that, go out of style after a season or 2.
So fast fashion for data objects.
Exactly. So generational collectors, they divide the heap into generations, like young, old, and maybe even, permanent new objects. They start in the young generation, and if they stick around long enough, they get promoted to older generations.
So like moving clothes from your closet to a storage bin as they become less frequently used, but you're not ready to get rid of them entirely.
That's the idea. And the clever part is that, well, garbage collection focuses mainly on the young generation, where most of the churn happens. This is, well, it's much more efficient than scanning the entire heap every time.
That's super smart. And finally, we have incremental collection. What sets this one apart?
Incremental collection is all about, well, minimizing disruptions. Traditional garbage collectors, they often stop the program entirely while they do their cleanup, which, well, can cause noticeable pauses.
It's like having to shut down the whole factory just to take out the trash.
Exactly. Incremental collectors, on the other hand, well, they work in small chunks, doing a bit of cleanup here and there while the program continues to run. It's more like, having a continuous cleaning crew that keeps things tidy without interrupting the main workflow.
So less disruptive and more efficient overall. This deep dive into garbage collection algorithms has been eye-opening. So much is going on behind the scenes to manage memory.
It's true, and understanding these different approaches, well, it can make you a more informed programmer, even if you're working in a language, with automatic garbage collection.
I feel like we've covered a ton of ground in this deep dive, from stack versus heap basics to memory leaks, fragmentation, and even garbage collection. It's clear that memory management is a pretty complex beast.
We have covered a lot, and I think our listeners, they now have a much deeper appreciation for how memory works in programming. But there's always more to learn. The Alco Academy post, it even goes into some even more advanced topics we haven't touched on yet.
Yeah, it's amazing how much depth there is to this topic. I think we've given our listeners a solid foundation to, well, explore those more advanced concepts on their own.
I agree. We've covered the essential building blocks. So let's bring this deep dive to a close. By recapping the key takeaways, we started by, well, comparing the stack and heap to a countertop in a warehouse, highlighting their, distinct characteristics and what they're best suited for.
Right. The stack is our speedy, organized friend for, well, temporary data, while the heap offers flexibility for larger or longer-lasting information.
Yep. We then explored, how different programming languages, they approach memory management, with some offering more direct control and others, well, taking a more automated route with garbage collection.
And we definitely couldn't skip over the common pitfalls, like stack overflow, memory leaks, and dangling pointers.
Yeah.
Those are important reminders of why, good memory management practices are so crucial.
Absolutely. We also delved into some of the trickier aspects, like memory alignment and fragmentation, showing how even seemingly small details can have a big impact on, well, on performance.
I think what's really fascinating is how much is happening, like, behind the scenes that we often take for granted as programmers.
Yeah, it's true. Whether it's the careful organization of the stack or the, intricate dance of garbage collection, there's a lot of clever engineering going on to keep our programs running smoothly.
So as we wrap up this deep dive into stack versus heap memory allocation, I want to leave our listeners with a challenge. Now that you have a deeper understanding of these concepts, how will this knowledge change the way you approach coding?
Yeah, how will it? Will you be more conscious of object lifetimes and choose the most, well, appropriate allocation strategy? Will you embrace tools like smart pointers to help you avoid common pitfalls?
And most importantly, will you keep that mental model of the stack and heap in mind as you write code, understanding how your choices impact performance and efficiency?
The Algo Academy post
Hmm.
that we explored, well, it's a fantastic starting point. And I encourage everyone to, check out the interactive tutorials they offer for a more hands-on learning experience.
Yeah. It's a great way to solidify your understanding and take your programming skills to the next level.
So until our next deep dive, remember to keep those mental stacks and heaps organized. And, well, happy coding!
Happy coding, everyone.